For year 12, I'm going to be just doing this whole big bumper PowerPoint because this takes us from the year 12 stuff that we were doing to the year 13 stuff that we will be moving on to. And obviously we're missing the exams, so we would have actually had a nice portion of time after the exams to move on. So this is what I would do when we come back into school and just check we're understanding. So we're going to look at rates, some of the images you've already seen before and some of the graphs you've done before, but I think it's important to practice them. So just quickly thinking, this starter task is writing down the factors that affect the rate of reaction and how we measure the rate of reaction. So you're going to need to make sure you can talk about surface area, temperature, concentration, the use of a catalyst or not, those kind of things, and how we measure the rate of reaction. We always use the equation, change in product or reactant over time, and it's always measured in centimeters cubed per second or grams per second, and it might be the amount that we've lost or the amount we've gained in product. And we would use it with continuous monitoring method, and we did some required practicals on those. So please do take your time over this. This isn't one lesson's worth. This is about 3 lessons worth, 4 lessons worth, and then you would have practicals on top of that. So this is quite a large proportion of work, and I wouldn't expect you to do it all straight away. So we've already done these graphs where we have looked at the steeper the gradient, the rate is at its fastest. So we've got a graph here that's concentration of reactant over time, and so the concentration is going down, and so we would do concentration change divided by time taken, so change in y over change in x. And the initial rate at t equals 0, so time equals 0, the gradient is steepest, so the rate is at the fastest. As the reaction proceeds, the gradient gets less steep and the rate decreases. When the reaction is complete, the gradient levels and the reaction is stopped, so there would be 0 rate of reaction. Maybe pause and sketch it. When we measure the initial rate, we're measuring the initial gradient where t is 0. So you would always draw your line, if you were working out the initial rate of reaction, from the initial gradient. And this is where we have our skill. Remember, I got you to practice those graphs. So there are a few graphs on here to practice. So here's one for you. You're going to need to pause this. It's going to take you some time. You will need some good square paper. If you haven't got any square paper, please let me know. I will post you a watch. You might want to plot it on Excel. Maybe that will work for you. You might actually be able to get it to do the gradient for you there. You'd have to be quite good at Excel, I think, or maybe I'm just rubbish at Excel, but you could maybe do that, or maybe print out some square paper, because it's really important that you understand how to do your plotting and your scales. So plot the graph of H2O2. So this is hydrogen peroxide decomposing spontaneously. So hydrogen peroxide, you've done this where you've put used catalase like liver and stuff to break it down into water. Draw the tangents at the start of the reaction, t equals 0, after 20 seconds and after 90 seconds. So you're probably going to be drawing, tangents because it's a curve. Measure the gradient of each tangent, so that's change in y over change in x, to work out the rate of reaction of these. Here is another one to have a go at. Okay, and it should look something like this. Now, I've got the calculations for these, so I suggest you do spend your time drawing these. I'm going to have to redraw the one on the previous slide because it's in the notes, so I don't know what they are, but it's worth having a go. So this one, I would say, definitely have a go at drawing it, and then work out your t equals 0 and t equals 3000. See where it's at 3000? They've used that plot, and see that the sort of gaps between the green and the blue line are equal on both sides when they draw their tangent. Okay, so at 0, change in SO2 Cl2 divided by time. So between 0 and 5, 0.5 and 0, that's the change in time. That's the change, not change in time and concentration, excuse me. And it's crossed the line at 3,300 seconds. So that's the change in x. And so you always want to be within a good 0.5 of these, because we're at 10 to the minus 4, so it's quite a large scale. Maybe I'd say actually between 0.2 out, I'd say. T equals 3000, so again, just read off your change in y. So that looks like, what, 3.75 there? 0.375. And then your change in y, where it crosses the y-axis. Now, Of course, actually, that's not crossing the y-axis, so you're going to need to draw a straight line from where it's extrapolated at the bottom. So here's mine. So my change in x is 4,000, and then, yeah, I said 7.5. So 0.38 minus 0.14, that's where the crosses the y. So check yours. Okay, so this is the bit that's new. So this is the orders. So this is the A-level portion. So the rate equation and orders of the reaction. So you've got to explain the terms order of reaction, rate constant, and rate equation. Now we've done rate constant. That was when we were using K. But you should be able to deduce the rate equation from the orders. So we need to introduce you to what order means. So what determines whether a collision between two particles will result in a reaction? I hope you're thinking in advance of me revealing the answers. The activation energy. So only particles that have enough activation energy will react when they collide. If we increase the concentration of a reactant, there'll be a larger number of collisions per second and a faster rate of reaction. By doing a series of experiments, we can work out how concentration of each reactant affects the rate of reaction, and how much they affect the rate of reaction, we give a figure to, and we call that an order. So mathematically, this effect is called the order with respect to the reactant. So for example, if I doubled the concentration, it doubled the rate of reaction, I would say it's first order with respect to whatever the chemical was called. But sometimes if you double it, it might quadruple the effect, or it might have no effect. So the order will tell us how much effect that will have, and we do that with a series of monitoring reactions. So this is the reaction. A plus B makes C. Easy. For reactant A, the rate is proportional to the concentration of A. So that means that means that if I double A, the rate will double. It's proportional. Or if I triple A, the rate will triple. So therefore, we've got rate is directly proportional to A, and the concentration is that square brackets, and the X is the order with respect to reactant A. So order is always defined in relation to concentrations. So there are only three orders that you have to learn. So let's try this one. A plus B makes C, plus C makes products. I would have written D there. I don't know why they wouldn't write that. So if something is zero order, if the order is zero with respect to A, the rate is not affected by the concentration of A. So if I doubled A in this fictitious experiment, if I doubled A, if I double the concentration of A, the rate of reaction wouldn't change. And so we would say that is zero order. Any number raised by the power of 0 becomes 1. So it would be constant and won't change. Let's have a look at first order. So first order is where if we double the concentration of B, the rate will double. It's equivalent and proportional. Any number raised to the power of 1 is itself. So if B increases by 2 times, the rate increases by 2 times. If B increases by 3 times, the rate increases. So that leaves second order. So second order, if the order is 2 with respect to reactant C, then the rate is proportional to C to the power of the concentration with respect to C. If we double the concentration of C, the rate quadruples, because any number raised to the power of 2 behaves like this. If C increases by 2 times, the rate increases by 2 to the power of 2, which is 4 times. If B increases by 3 times, the rate increases by 3 to the power of 2, which is 9 times. So it's squared numbers. Excuse me. So, same example. So let's move on to look at the rate constant. So the orders of the reaction with respect to the different reactants are as follows. So the order with respect for A is 0. The order with respect to B is 1, and the order with respect to C is 2, or second order. So the rate is affected by the concentrations as follows. So the rate is with respect to A is 0, so remember the square brackets means concentration. So if we combine those expressions, we get this. The rate is proportional to A with respect to 0 with respect to A, 1 with respect to B, 2 second with respect to C. The rate constant is a proportionality constant that links the rate of reaction with the concentration of the reactant. So we've already kind of done this when we were looking at K, the rate constant, but in this we're focused on rate. So the rate is equal to K, the rate constant, multiplied by A, which is 0 order, B, first order, C, second order, which we would simplify because A is 0. A is not affecting the rate of reaction at all, so we remove it from the equation. So the rate would become rate equals K, B to the power of 1, C to the power of 2. So the overall order is the sum of the individual orders. So the overall order of this whole reaction is 3. We just add them up. The orders of reaction can be found from experimental results only. They can't be determined by balancing the numbers in a reaction. So you can only find them by doing experiments. Right, let's have a look at these questions. Pause this and then have a go, and then the answers are going to be on the next slide. Just so you're aware that obviously P is second order and Q in the first one is first order. We don't write the one because it's obviously in relation to itself. So have a go at those. I'd say the complicated one here for the first question is C, because obviously if both of the concentrations are changed, what's going to happen? And then the other is you're given information and you've got to deduce the orders from the information from the experiments. Have a go at those. Okay, oh, that's a shame. I'm a bit annoyed that the answers come straight up on this. So P is second order, so the rate quadruples. Q is first order, so the rate will triple. P and Q are both tripled, so therefore P is times by 9 and Q is times by 3, so we combine both of those. 3 times 9 is 27, so they'd be multiplied, and then we've got in the reaction between Q, S and T, so if R is doubled, the rate is doubled. If R is doubled, the rate is unchanged, which means that is 0 order. If S is quadrupled, the rate increases by 16 times, so that's second order. And if T is halved, the rate is halved, so that is going to be first order. So if we're writing that down, rate equals K, S concentration, second order with respect to S, and then first order, and so overall order is third order. So we've already done a bit on finding the units of K. So the units of the rate constant depend on the overall order of the reaction. We can determine that by substituting in the units into the rate equation. So we've already done this when we were looking at the rate constant. So here's some examples. So rate is equals K, concentration is 0 order with respect to A, so the rate is just K. So remembering that K is a rate constant, so it's going to be moles per dm cubed per second. And then to the -1 because it's per second, so it's on the bottom. So if the rate is K is A, so therefore first order, it means that K would be the rate divided by A. So therefore, well, the units of K would be, so the units of K would be the rate divided by A, just rearranging the equation, cancel out the moles per dm cubed, seconds to the -1. So if it's second order, it's essentially like saying times by itself again. So again, put them in brackets, put them on the bottom. So this would be dm cubed moles to the -1, seconds to the -1. And then if we've got something that is more complicated, so we've got a second order in there and we've got a first order in there, then again, it's squared and then again times by another. So it's exactly the same way we worked out the units of K before, but we've just got to stick rate across the top. So make sure you've got examples of that written down in your book. And here's a question. First one to have a go at. So pause this, have a go. You should have this. So if we want to make K the subject, so it's the rate divided by the concentration of ozone and ethene. And they've given you They've given you the concentration, so you're using actual data now with these. And you should get 2000 moles per dm cubed to the seconds to the -1. Okay, this is another lesson, so you might have wanted to have taken a break. If you have, welcome back. So this one is about half-lives. So using the terms order and half-life. So you've probably come across the word half-life before when you were looking at physics, probably. So looking at radioactivity and the half-life of radioactive isotopes. Similar, actually, to be honest. So you need to know your order stuff from last lesson. So you should be able to plot a concentration time graph. If you can't do that, go back to the beginning. There's loads of examples in your book. Have a go. You've got to start being able to produce the rate. Working out the orders is going to be coming up on this one. So the half-life of reaction is the time it takes for the concentration to reduce by half. So when you did radioactivity, when you're in year 11, you knew that the half-life of radioactive isotope is the time taken for it to reduce in radioactivity or radioactivity by half. So for a first order reaction, the half-life is constant. So if it reduces in concentration in 10 seconds, then by half in 10 seconds, then to reduce it by half again, it will take another 10 seconds. So half-life is the same regardless of the concentration. Here the half-life is 53 seconds and it's consistently 53 seconds. The shape of the graphs is really important as well. So zero order, the concentration decreases at a constant rate. Half-life decreases over time. For first order, they are constant, and then for second order, it's much rapid. So actually, the shape of the graph can quite often give you the answer to the half-lives. Here's a couple of questions. Have a go at. Pause this video because I'm going to pop the answers up in a second. So this first question, hydrogen peroxide reacts in first order with a half-life of 27 seconds. If the initial concentration is 1.6, what's the concentration after 81 seconds? So you should be 81 divided by 27 is the half-life, and then divide that. So obviously you're going to go to 8, then to, 0.8, 0.4, then 0.2. Paracetamol has a biological half-life of 380 seconds. How long will it take for the level of paracetamol to fall to 1/16? So one half-life is 380 seconds, 2 half-lives is another 380 seconds. So adding them all on top, you should have 1,520 seconds or 25.3 minutes. Another lesson, so finding the order from a rate versus concentration graph. So instead of concentration time, this is rate concentration. So have a look at these. So we've got a rate concentration. So if concentration is on the x-axis and the rate is on the y-axis, if it's zero order, you'll have a straight line. If it's first order, as the concentration increases, the rate increases, much like we know about the orders. And second order, it's times 2 by 2 by 2. So in this case, it will be a curve upwards. Draw those. Okay, so here's a really good example is the clock reaction of showing how we work out the initial rate. This is practical we're going to do. I think we did do this actually, potentially. But this is a really good example. So here's a worked example. So this one you did probably for GCSE, where it caused a cloudiness, precipitate, couldn't think of the word, and you time how long it takes for a certain amount of precipitate to be seen, and we would do an experiment where we kept the concentrations the same, and then we would change one, maybe the hydrochloric acid or the sodium thiosulfate, but you keep the other the same, and then you would time how long it took for a certain amount to be formed, and the initial rate would be 1 over the time taken for it to form. So this is another way we can work out the initial rate, is you just time it and then do 1 divided by, because if you're keeping the concentrations constant, then in theory they should the time would be the variant that you can then use to measure on the graph. So the rate of reaction depends on both the rate constant and the concentrations of the reactions present in the equation. So the larger the value of K, the faster the rate of reaction. That's really important. Write that down. Fast reaction has a large value of K, a slow reaction has a small value of K. The key factor in the rate of reaction is the number of collisions that exceed activation energy. So rate increases with temperature by much more than can be explained from just an increased frequency of collisions. So if the rate increases with T while the concentration is unchanged, then K must change with T. So therefore the value of K must change if you increase the temperature because the rate changes. So increasing the temperature speeds up most reactants by increasing the value of K. For many reactions, the rate doubles as the temperature increases by 10, but not all of them. And this is because more particles have above the activation energy. Here's an example as if you increase the temperature, what happens to K? This is the final part, and again, this would be another lesson and we would look at some reactions. So this is about the rate determining step, and I always think about this as what's the thing that's slowing it down? That's essentially what the rate determining step is. When you look at a mechanism, how do you work out what the rate determining step is? So many reactions take place in a series of steps. They don't go A, B to C straight away. They might go A reacts with B to make a B plus, and then that breaks down to make a C. So multi-step reactions often have one step that's slower than the other steps. The slowest step is the obstacle for the whole reaction, and the overall reaction will be no faster than the slowest step. So a really good example for this is I always think about if you've got 4 elves working in Santa's workshop. Let's say you've got one making the gifts, one wrapping the gifts, and one labelling the gifts. If the guy making the gifts is the quickest, so let's say he can make 100 gifts in a day. Let's say that the second elf can wrap 50 gifts in a day. And let's say that the labelling elf can label 100 gifts in a day. So the wrapping elf would be the rate determining step, and so therefore the rate would be 2 days, or 50% of the gifts per day. So the rate determining step is the slowest step in a reaction. Okay, here's an example. So we've got NO2 plus carbon monoxide makes NO plus CO2. The overall equation doesn't tell you about the mechanism. You have to carry out experiments to do that, or you have to suggest them. If this experiment's carried out and the rate was this, what are the orders of reaction with respect to the two reactants? So NO2 is the second order with respect to NO2, but CO must be 0 because it's not in the rate equation. See? If a reactant appears in the rate equation, it must participate in the rate determining step. So CO isn't involved in the rate equation, so it doesn't take part in the rate determining step. The order with respect to that reactant tells you how many particles of that reactant are involved in the rate determining step. So NO2 plus NO2 is the slowest part because it's in the rate equation and it is the rate determining step. Okay, so the rate determining step involves 2 molecules of NO2. The rate determining step must be followed by further series of steps. Together, the sum of all these steps add up to give the overall equation. So that's the overall equation in blue there. So you can propose a 2-step mechanism. And so you kind of summarize what you know. So you know that the rate determining step must include 2 molecules of NO2. So what could they make? Oops. Skip forward really fast there, sorry about that. And we know that the second step therefore the non-rate determining step must include carbon monoxide. So how are we going to get from what we know to what we had to begin with? So the other reactant in the second step must be NO3, so that the products of the first step must be NO and NO3, so that they can react together to form what we've got. So at the bottom, combined mechanism NO2 makes NO and NO3. And then NO3 plus CO makes NO2 plus CO2, which is, as we know, the final step of... no, it's not the final step, but it's the next step in the overall equation. So NO3 is an intermediate. It doesn't appear in the overall equation. It's generated and then used or consumed during the mechanism. Okay, it's final couple of questions for you here. This is the last one. So the rate determining step of reaction between X and Y is Obviously, we have to do experiments to work out the rate equation. But based on this, if that is the rate determining step, then the rate equation is going to be X second order, isn't it? Because it's got 2 molecules of X. So therefore, boom. So the next one, predict the rate equation. There's that. Explain what is meant by the rate determining step. So it's the slowest step of a mechanism. What does the rate equation tell you about the rate determining step? So let's look at the rate equation. So 2 molecules of NO take part in the rate determining step. Suggest a possible 2-step mechanism for this reaction. I'm going to have to pause this and just write it down myself. Okay, so I've just got my pen and paper out so that I can do this because there's no answer on the bottom of this. Poor planning on my part. So we know the rate determining step has got NO plus NO in it. And so I worked out that would make a molecule of N2O2. And then if we have N2O2 plus O2, that reacts together to make 2NO2. Boom. Done. Loads of questions in your book about this if you need help.